All right, so I'm trying to figure out what happened here. If you look, I got an answer of 56 and I know something's wrong. So if I look up here, I see 56 in 2 of my lists, but it sure doesn't appear in my 6s. So I want to go back and double check that I got everything from my factorizations correct. 1 was my greatest common factor. There is a bundle of 2s. I do see this extra 7. I already took care of this, my bundle of 2s. There is an extra 7, and there are 2 extra 2s. Oh, I see it now. I forgot to include times 3. This looks better. Well, 3 times 56. Sometimes I break this into parts. We call it partial products. 3 times 50 is 150. 3 times 6 is 18 more. So 150 plus 18, 168. Well, that makes better sense because I sure didn't see any common multiples in my multiple list. And maybe if I kept on going, I could get to 168. A way to kind of double check this would be, does it divide by 6? I bet it does. Does it divide by 7? It should. And does it divide by 8? Actually, if you did some checking, 8 goes into 16 twice, 8 goes into 8 once. It absolutely would go in there 21 times. So it does divide by all 3 numbers. This checks out. I would love to say that there are 168 marbles and say, ta-da, problem. 168 marbles, that works because it divides by 6, 7, and 8. But let's go back to this detail that we kind of were saving for later. This was kind of a later thought. I have 4 marbles left over each time. I need 4 more marbles mixed in here somehow. How am I going to show more? Well, the answer would be with addition. I need to add 4 marbles extra. And if you choose to stack this, you could, or I would say 168 plus just 2 would get me 170. Plus 2 more would get me 172 total marbles. When I say word form, I really mean make sure you have your labels on here. And maybe someone really wants to get involved and they want to give me a nice sentence which says, the box of marbles must have 172 total, or something along that line. All right, let's see if we can look at number 32, and I hope it goes a little better. I hope I don't make this mistake like I did a minute ago. So here we go. We have a light flashing every 2 minutes, and a second light flashing every 3.5 or 3 5/10 minutes, and a third light flashes every 4 minutes. If all 3 lights flash together at 8 p.m., what is the next time of day they will all flash together? This is important. I have 3 lights. One's flashing every 2 minutes, one's flashing every 3.5 minutes, and one's flashing every 4 minutes. Well, if I think about that, they all turn on at the same time. They all blink. And that's cool until they start blinking at random. I wish I could figure out the next time. Well, as time passes, time moves on. There's more time that I'm using up. It sounds to me like I need more of something, more time. So when I think of more, I tell the students to think of multiples. So could I find the multiples of 2, 3.5, and 4? And could I look for something that they have in common so that I would find the next time that they'd flash? That's what we'd like students to do. So I would count by 2s. I'm running out of room here. Hopefully that's enough. We'll show it to be continued. This 3.5, it wouldn't be very fun to put on a tree, so I think we're going to have to try it this strategy. 3.5 times 1 would be 3.5, or 3.5. Someone might want to think of this as money. You could call it $3.50. If I doubled that, well, I'd have $7, or 7.0, or 7 0/10. If I added another 3 to this, let's see, that would be 10 and 5/10. You have to remember that half at the back, that 5/10. Well, if I had 10 whole dollars and I give you 3 more, that would make 13. And my 50 cents and 50 cents would make another whole dollar. That'll get me 14. Next I have this 14 and I'm adding 3.5 to it. Looks like I'm going to get 17.5. Do we see anything in common yet between these two lists? Ooh, 14. That might be a good choice. Let's go a little bit farther in case it's not. Well, 17 plus 3 more, the whole numbers, would get me 20. And these decimals, 0.5 and 0.5, that's the same as 1 whole. So 20 plus 1 more, 21. 21 plus 3.5 would get me 24.5. Or 21 plus 3 gets me 24. And a half and a half, sorry, and only one more half, 24.5. Now I have 24.5. I'm adding 3 more. That'll get me 27. And when I combine those halves, it looks like I'll get 28. Let's go as far as we can here. 28 plus 3 more is 31. And I have to remember to add that half back on. Let's try one more. 31.5. 31 plus 3 more is 34. And I have this half plus the half over here. Well, 34 plus another whole would get me 35. This is going to continue for a while. Let's try 4s. That should be faster than our decimals. Any matches so far? Ooh, 16. No, it's only in 2 of the numbers. 14, only in 2 of the numbers. I guess we have a ways to go here. Oh, hold up. I think I see something. There's a 28 here, and here, and here. Is there any smaller number that they all share? Doesn't look like it. Looks like 28 might be my least common multiple. So the first multiple that appears on all 3 lists would be what we call the first common multiple, or the least common multiple. So I'll call that 28. So how does that help me? Well, if I go back to the problem, they're talking about minutes, right? So it takes 2 minutes for the first light. It takes 3.5 minutes for the second light, and 4 minutes for the third light. This is talking about 28 minutes before they all flash again. So I wish that was the question. If all 3 lights flash together at 8 p.m., what is the next time of day they will all flash together? Well, if it's 8 p.m. when they first flash, I want to add 28 minutes to that. 8 p.m. is like saying 8 o'clock p.m. and I want to add 28 minutes. Oh, 28 minutes would kind of look like this idea. It kind of looked like a 28 happening in the minutes. So if I were to combine those, it looks like I'd get 8:28 p.m. That's actually my answer. 8:28 p.m. It has a label. I probably would do better to say all 3 lights will flash together again at 8:28 p.m. The last thing I left off was this ladder idea. And again, I don't think ladder is very great when we're talking about decimals. That could be kind of challenging to handle today. But what we could do is try a quick ladder with 6, 7, and 8 from our last problem. So if you're a ladder person, we'll just show you one quick step if you would like to see it. 6, 7, and 8. If not, you can just stop my video whenever you like. So if you look here, I don't have any prime numbers that go into all 3 digits, but I do have a prime number that goes into 2 of them. It's kind of like taking out a pair. First I try to take something out of all 3, a triplet, and if I can't do it, then I find something that will just go into a pair of the numbers. Well, 2 goes into 6 3 times, and 2 goes into 8 4 times. But this 7, it hasn't changed at all. It comes down. If you take a look, what I'm left with in this L of my LCM is exactly what I need to multiply. 2 times 3 would get me 6, and 7 times 4 would get me 28. So 6 times 28. Well, let's see. 6 times 20 is 120, and 6 times 8 is 48. 120 and 48 more. Oh my gosh, I got the same great answer as earlier. So again, ladder method, I like it because it's quick, but not all students are comfortable pulling out, first of all, a prime factor that goes into all 3 numbers, or what I might call triplets, or a prime number that goes into just the pairs next. So just a strategy for some of us who are more comfortable with ladders. Hopefully this was a little bit helpful working with LCM and common multiples. And I know these word problems are tough. Something more like this, number 32, appears on their test, which is happening soon. And this other one is really a challenge. I'm not sure that we're going to go there for the test, but good information for someone who's a higher level thinker. Maybe they can get to an answer. And if your student's struggling, if they know the right strategy to apply and they get stuck along the way, they're still in a good spot, and we just want to encourage that thinking, because the more they see these, the more comfortable we become and the more they grow.